This is a server room project by Group 21. Members are Omar Awadallah, Matteo Bovino, and Ayub Aldam. I am Matteo Bovino and would like to talk about the key aspects of the project, including flowchart, components, design, code, and overview. In the flowchart, we can see the common starting point, which is over here. When we boot up the system for the first time, we are going to check if the setup function has been done. If it has been done, we are simply going to skip to the start of the cycle, otherwise we're going to store the number of users and passwords in the E2P ROM. The main, as you can see in the start of the cycle, we have three operations happening at the same time. The main one is the voltage reading. So we're going to take the input voltage, compare it to a threshold, and depending on the value, if this value is below the threshold, we're going to turn on the power supply, which is a backup. Otherwise, if it's above the threshold, we're going to simply keep the power supply off. While we do this, we're also taking a temperature reading, and this is working thanks to interrupts. So whenever a 5-second pass, an interrupt is triggered, and we're going to take a temperature reading. If we don't have 5, we're going to keep doing this until we have 5 readings available, and we're going to average them. If the average is bigger than 20, we're going to turn the AC on, otherwise we're going to add with the average and reach the end of the cycle. At the same time, we're also going to check the passwords. So if a password has been inserted in the last 60 seconds, we're going to check if it's correct. If it is, we're going to grant access, otherwise we're going to output a message saying to try again later. If no password has been inserted, we're going to take the password from the user and again compare it and check if it's correct. If it's not, we're going to block the room and access to the room for a whole minute, otherwise we're going to grant access for a whole minute. These are the individual components that we have utilized in the system. The microchip controller is the key component here. It's a central processing unit, and here conversions, calculations, and ALU operations are taking place. The Bluetooth module is also really important because it allows for the device, allows the system to communicate. The communications are wireless. Another Bluetooth module or Bluetooth device is going to pair with the Bluetooth module placed on the system, and they're going to transmit information that are going to then be fed to the microchip controller. The LM35 sensor is our temperature sensing module. Its operating range voltage is 4 to 20 input volts, and it is connected directly to the microchip, to the PK18. Its values are shown through 3 7-segments displays. We decided to use 3 7-segments because we want to have 1 decimal accuracy. Depending on the values from the sensor and the Bluetooth module, we are going to turn a variety of LEDs on. For instance, this red LED is turned on whenever we deny access to the room, and the blue LED and the green LED and the yellow LED also show the status of the system. The hardware and product design that I wanted to include is the PCB design and the Proteus design. I would like to highlight the differences between these two. In the Proteus design, we have potentiometer over here, and this is used to represent voltage fluctuations in the simulations. However, in the real system, in the PCB design, we don't have to represent these voltage fluctuations. We simply have to add a pin that's connected to the ADC port of the PK18. The virtual terminal also is not included in the PCB design. We actually have included the pin out for the Bluetooth module. These changes are important, especially in the PCB design, because more components require more complex routing. As you can see here, I decided to add a top layer red one, indicated by the red color, which is important because it allows me to cross other routes, and this allows for a simpler and more clear connections. The code that we have developed includes many structures, and one that I wanted to highlight is the for loop here. This for loop is very important in the system because it allows us to store 4 digits for each password, and it's also really simple and clear. Whenever we do one iteration of the loop, we're going to change address, get the value from the user, convert the value by subtracting 48, so it's no longer an ASCII, and then we put this value in the EPROM address. When we do 4 iterations of the loop, we're going to have 4 digits, and this is a 4 digits composed of one singular password. Another structure that we use a lot is an array. As we can see here, we have a result array and password array. Both have variables as indexes because we want to have dynamic arrays, so we don't have to actually physically specify each place, but we simply use a variable. So whenever t changes, we're going to change the position in the array, and we're going to store a different value in that position. In the compare function of the code, we are checking the password, and we're not checking a single digit, but we're checking the whole sequence. That's why we're using the EE logic operator to make sure that the whole password is correct. Depending on the result of this comparison of this if statement, we're going to turn different bits of port C that are both connected to specific LEDs, and so we can show the status of the system using these bits, using these LEDs. The timers are also a crucial part of the code and of the system. Timers, however, don't have a limited space, and therefore we cannot have one timer represent, for instance, a whole minute. We have to use the same timer multiple times, and that's why we have the variable overflow over here. This variable is make sure that the timer actually triggers 600 times before completing the interrupt service routine. As explained here, 10 overflows are just 1 second, therefore we need 600 overflows to form 1 minute. We have explained the calculations in the report, where we have included the maths behind this, and also why we have preloaded the timer with 3036. This is just to have accurate timers and accurate time frames. A general overview of the project. The system is capable of doing everything that we expected, so both in simulation and practice. We also are capable of having different hierarchy and different organizational power in the system. For instance, we have users that are simple normal users, and also admin that are capable of doing capable of having more organizational power in the device and making more changes. We also noticed that some simple modifications could have improved the capabilities of the system. For instance, we thought about adding motion detection and flood monitoring. We noticed that this was not going to be cumbersome. However, it would have required changing the pinout and the connection to the microcontroller. However, this is something that may be kept in mind for future development. In the full report, we have also included assessment regarding the longevity of the product, the safety and health considerations, and its market release.